Concrete is a frequently used construction material because of its relatively low cost and freedom of design. Despite its proven benefits, concrete often exhibits cracks which appear due to excessive tensile stresses. Via these cracks, aggressive substances enter into the concrete, causing concrete degradation and reinforcement corrosion. Repair of these cracks is very labor-intensive and thus expensive. At the University of Ghent, Professor de Beely and her team are developing self-healing concrete. The use of this type of concrete will extend the lifespan of the construction and will lead to more durable concrete. In a first phase of this study, superabsorbent polymers are used, a kind of hydrogel particles. These polymers can take up a huge amount of water and swell. These particles are added to the concrete during mixing. When a crack appears in the hardened concrete matrix, the polymers are exposed to a humid environment and swell so that the crack is blocked. However, in dry periods, the superabsorbent polymers will shrink again, and only after deposition of solid healing products, the concrete crack can be blocked in the longer term. Superabsorbent polymers are located in the pores of the concrete matrix. When a crack appears in the concrete, it goes through the pores with superabsorbent polymers. As water enters into the crack, it is absorbed by the particle. The particle swells and blocks the crack. In a second phase, bacteria, which are able to precipitate calcium carbonate, are embedded in the concrete. These crystals are deposited in the crack, resulting in crack closure. Due to this, aggressive agents can no longer enter into the crack and the durability of the construction is improved. As the bacteria need to survive in the concrete without nutrients until the moment that the crack appears, they are added to the concrete mix in a dormant state. These dormant bacteria become active as soon as they come into contact with nutrients and water, which intrude via the crack. However, these bacteria cannot directly be added to the concrete matrix, as they would be crushed in the small concrete pores during hardening. Dormant bacteria are embedded inside concrete. A crack appears in the concrete matrix. When water enters into the crack, the bacteria become active. The bacteria convert the nutrients into calcium carbonate and repair the crack. When these bacteria are combined with the superabsorbent polymers, a very efficient way of self-healing is obtained. On the one hand, the superabsorbent polymers protect the bacteria. On the other, the water which has been taken up by the hydrogels can be used by the bacteria to precipitate calcium carbonate. While these superabsorbent polymers induce an immediate but temporary crack closure, bacterial calcium carbonate precipitation results after a while in permanent crack closure. Both techniques thus complement each other very well. Dormant bacteria are embedded inside concrete surrounded by superabsorbent polymers. A crack appears in the concrete matrix and activates the bacteria. The superabsorbent polymers swell and block the crack immediately. The bacteria precipitate calcium carbonate inside the crack, which repairs the crack in a permanent way. The superabsorbent polymers returned to their original state. The efficiency of this technique can be modeled or demonstrated by means of various test methods. In a first experiment, a graphical reproduction of the crack appearance is obtained. By applying a speckle pattern on the surface of a concrete beam and by the use of two cameras which are set up under different angles, minimal changes at the surface can be registered. By using this technique, we can detect stresses and crack openings at the surface. In addition, sensors are placed on the surface which capture acoustic waves and can thus detect the crack development. Self-healing has proven to be efficient when a new crack appears at the moment the beam is reloaded, and as new acoustic waves are recorded showing the regain in strength. A second experiment is a water permeability test. Due to the fact that the hydrogels start to swell at the crack faces, less water enters through the crack if someone compares it to a specimen without hydrogels inside. Finally, self-healing can be proven by means of computed tomography. Similar as in medical research, a complete X-ray scan is made of the sample. After image analysis, the precipitation of calcium carbonate inside the crack becomes visible. The research, which is done at the University of Ghent by Professor de Beely and her team, aims at an economical and durable improvement for our society. It will no longer be a utopia that concrete structures are able to repair themselves, as it is the case for biological materials.